On October 6, 2017, it was announced that the Peace Nobel Prize for this year goes to the ICAN, the International Campaign to Abolish Nuclear Weapons, for its work to draw attention to the catastrophic humanitarian consequences of any use of nuclear weapons, and for its groundbreaking effort to achieve a treaty-based prohibition of such weapons. But what makes them so deadly? And more importantly, what exactly is a nuclear bomb? The nuclear bomb is by far the strongest, most destructive weapon humanity has ever created. When the largest of them, the Tzar Bomba, was detonated, it released the energy equivalent of 58 million tons of TNT, which is as much energy as the entire population of Austria consumes in an entire year, which is a lot. But how exactly do they work? Nuclear bombs exist thanks to one physical phenomenon: nuclear fission. Fission happens when a neutron is being shot at a heavy atom, usually it's uranium-235 or plutonium-239, causing it to split into two smaller atoms. But there's a problem. The combined mass of the byproducts is smaller than the parent atom's mass. So where did the missing mass go? Well, we know that E equals mc squared, which means that a little amount of mass can be converted into a huge amount of energy. And that's where the missing mass go. It was converted into energy in the form of intense heat, light, and radiation. However, the fission reaction in one atom doesn't release much energy. What happens inside a nuclear bomb is a fission chain reaction. Here's how it works. Let's use the uranium-235 atom for the example. When a neutron is being shot at the uranium atom, it splits into a barium-141 atom, a krypton-92 atom, some energy, and 3 neutrons. And those 3 neutrons will then hit other uranium atoms, causing them to split and release more energy and even more neutrons. And so, the chain reaction continues. And it is very, very powerful. If you split 1 kilogram of uranium atoms, an entire gram will be converted into over 83 terajoules of energy, which is as much energy as the average human body consumes in an entire lifetime, times 367. However, most of the uranium doesn't split in regular chain reaction. In a nuclear power plant, only 5% of the fuel is being used, so you would actually need way more than a kilogram to release that much energy. But how do you trigger the reaction to make a bomb in the first place? The idea is to turn a subcritical mass of nuclear fuel into supercritical, causing the fission reaction to grow exponentially and then... There are 2 common types of bomb that trigger the reaction in 2 different ways. The first one is the gun type. And it works like this. You take a hollow cylindrical uranium bullet, which is subcritical, and shoot it at a cylindrical uranium target, which is also subcritical. But, as the bullet arrives at the target, they form together a supercritical uranium cylinder, causing the bomb to explode. The other one is the implosion type. You take a subcritical sphere of plutonium-239, surround it with conventional explosives, and explode all of them simultaneously. The explosion causes a pressure wave that causes the plutonium to dramatically increase in density, which turns the plutonium into supercritical, which again triggers an explosion. And those explosions are huge. This is the explosion of the bomb Umbrella, an 8-kiloton atomic bomb detonated underwater in the year 1958. This is the explosion of Ivy King, a half a megaton nuke detonated in the year 1952. The mushroom cloud reached an incredible height of over 17 kilometers, which is higher than the flight altitude of a commercial aeroplane. And this is the Tzar Bomba. As I said, the largest nuclear bomb ever detonated, with an explosive yield of over 58 megatons. The mushroom cloud reached a height of 62 kilometers, and it caused windows to break in places as far as Norway. But there's another side of the bomb, a side effect as scary as those humongous explosions and the deadly X-rays. I'm talking about the nuclear fallout. When any bomb is detonated, it releases dust everywhere. Same goes for a nuke. Except this dust is highly radioactive. And because the dust can reach an altitude of tens of kilometers, where wind speed can be very high, the radioactive dust can spread and land hundreds of kilometers away of the blast. Besides the high radioactivity that can give you a severe radiation sickness, there are other things in the fallout that can kill you, like strontium-90, a highly radioactive element which gets absorbed to your bones and teeth due to its similarities to calcium, causing bone cancer and leukemia, and the ejected neutrons that can hit your DNA molecules, causing genetic mutations. There's also the story behind the bomb, which is as interesting, but this is for another time. For now, I hope you all understand why the ICAN won the Nobel Prize this year. I'll see you all in the next video. Bye! Time flies when you're having fun. Everybody knows that. But why? And how? And can time really go faster or